Well, thank you very much for this opportunity. So, my research is on minimizing difficult optimization problems. So, I work on developing algorithms to find at least local solutions of landscapes that can look very nonlinear and very non-convex, that could have a multitude of minimizers of all sorts of quality, and yeah, that could be really highly oscillatory and have very strange shapes. So non-convexity is this kind of notion that encompasses everything, but I assume, at least in this talk, that my underlying function is somehow smooth. So this incorporates a huge number of real-life problems occurring in a wide array of applications. I don't have really enough time to go into a lot of applications now, but we try to develop generic tools that can solve this kind of problems. And what we want is to be able to maybe have answers given to us by a black box. So it may not be, we don't need to know much about the landscape. Ideally, we would like to have at least first derivatives as well. But we'll see a bit later on that we can give up on that requirement as well. So imagine that f is given to me in a black box, that I just give some kind of point, I query the box at some point, and then I get back f of x and maybe derivatives, and then I can proceed with my algorithms. So also, we would like to be able to take in any arbitrary guess, and this is what these methods do. You can start from any sorry, there is no pointer, sorry. Yeah. So there is no assumption on the initial guess. So what these methods do is you start somewhere, you just say, okay, this is my initial guess of my solution, and then I'm going to refine that guess iteratively, using at each iteration problem information. And more specifically, at each iteration, what I will do is I will approximate my complicated function by something simple, and just minimize that simpler model instead of my complicated function. And minimizing that simpler model gives me another guess of the solution. Things are a bit more complicated than this, but that's the idea, that I'm going to approximate by something simpler and minimize that instead. There are many techniques already there, and I don't know how much people are aware, but there is a lot of powerful software that can actually solve large-scale problems that can operate on this kind of principles and use all sorts of any black box to give the function values and gradient values. So this is really, maybe people think that in the presence of non-convexity we can't do very much, but in fact we can. I think that's the first thing to say. So indeed, this is a very well-researched area, and my research contributions in the last few years have been on being able to say more about these methods. So what we know, there is good software. There is also has been good theory that tells you from an arbitrary initial guess you can converge to a solution. You can get it, but people haven't been able to say how long will it take to converge. So the question on what is the rate of this convergence has not been studied for non-convex problems. This is something that people know very well when your function is convex, but for non-convex, people thought this was an impossible kind of analysis to do. This translates into how long will I have to wait for my computer to terminate and to get within some, thank you, within some accuracy epsilon for my solution. In other words, also I can rephrase this as, what's the complexity of my method? How many evaluations, how many calls to the black box do I need to make from any initial guess to get to the solution? And we were able to investigate most methods that exist and found that they are not very good from this point of view, and able to come up with optimal methods from a complexity point of view. So this is what I will review in the first part of the talk, and then I will go on to talking about what if I don't have accurate information about my problem. Because for large-scale problems, computing an entire gradient may be way too expensive. For example, in machine learning, I would not want to have to do that. So then I will talk about what if I have stochastic data or if I have incomplete data somehow. And I will say what happens to these methods. So I will keep talking about the same kind of methods, but in this kind of framework of even larger scales than classical Right, so things will get a bit technical here, but maybe ignore the slides a little bit and just listen to how I'm trying to explain them. So I will have a smooth function, and I'm just telling you a bit about complexity of standard optimization methods. So I'm starting from any arbitrary guess, the method that maybe you've heard of called steepest descent that moves along the negative gradient at each point. So we quantified, so this has been quantified a bit, and we have found that to get a small gradient, to get within epsilon of a solution, you take on the order of epsilon to minus 2 function evaluations at most. At most this many to get to a solution. So this indeed seems quite pessimistic. This corresponds to a sublinear rate of convergence for the algorithm. And you could say, okay, but this is just a bound. We actually were able to show on a one-dimensional example this bound is actually sharp. So you can't do that better than this for steepest descent method with any sort of globalization procedure or any variant we know, really. We can't do better than this. So in this one-dimensional example, we constructed a function on which this bound is attained. And you can see here the gradient, how it oscillates and it converges to 0 at infinity. And then on this example, you can show that this bound is actually attained. So we can't do better for steepest descent. But how about, maybe you've heard of Newton's method, the fastest method in optimization, really. Newton's method is as bad as steepest descent from a complexity point of view. This is perhaps somewhat surprising. We know that if we are close to a solution, Newton is very fast. But if you're far, actually is no better than doing gradient methods. So again, we constructed an example to show that even Newton on quite a smooth function that is even C2 and has a Lipschitz continuous Hessian and so on. So it's a very nice function, actually. Newton attains this kind of bound. So because most methods, all these linesearch trust region methods are based either on steepest descent variance or Newton variance, in fact, all these results apply for any general method that we know. So any kind of framework with linesearch or trust region that is standard, these bounds apply. So the worst case complexity of nonconvex optimization, classical nonconvex optimization, is epsilon to minus 2, whether it's a first order method or a second order method. So there seems to be some kind of blindness when you have this global behavior, when you look at the global behavior between the case of a first order and the second order method.
Could you go back to last slide, please? The black line on the left, is that the trajectory of the...
yeah, the points here are the iterates, yeah. So the question is there anything better? And could we, if we use higher order information like second derivatives, can we do better than steepest descent for non-convex problems? And the answer is yes. Okay, so the idea is, simply put, use a different local model than we've used before. So instead of doing a pure second order model, use something regularized and something with a cubic terminate, and minimize that to find your next guess of the solution. And of course, these algorithms are more involved, really. What you need to do, you need to not just minimize, you need to see, does the function make progress when you minimize the model? If it does, then you take the step, otherwise you stay at the same point. And if you can't make progress, then you have to adjust your model, and you penalize here more the length of the step to make sure your model is a better representation of your function. The mathematical details are really just in case you're interested in this. But the idea is use a different local model involving regularization, and then develop a coherent framework with that. And what happens is that the complexity improves to epsilon to minus 3/2. Still sublinear rate, but it improves to epsilon to minus 3/2. And if you have exact second derivatives, you can get things more easily, but still the same complexity. And you can do even approximate second derivatives to get this complexity. So better than epsilon to minus 2. Again, this bound is sharp. Again, we have univariate examples on which this bound is attained. But we were able to go further than this and to say that, in fact, there is no better method in terms of worst case complexity than this kind of cubic regularization ideas for non-convex optimization when you have second derivative. So Newton type methods, there is no better Newton type method than this from a complexity point of view. So this is an optimality result, really. Okay, so does it work in practice? We have a way to represent performance profile, to represent performance of algorithms through performance profiles in optimization, and we've compared sort of cubic variance with, say, trust region, a standard approach, and the higher the curve, the better the method. So it does seem that, on average case, it also seems a worthwhile approach. Right. So this has, in the last few years, this has been a lot of my focus of research, trying to characterize non-convex optimization algorithms from this point of view. Okay, so now I want to talk about a slightly different framework built on these frameworks, on these algorithms. And that is, what if I don't have accurate problem information? Right. So if I don't have derivatives, there is an entire area of optimization called derivative-free optimization that deals with developing algorithms for this context. So just function values, no derivatives. And it doesn't do finite differencing. It does something more sophisticated. But I want to go a step further than that. So I have this kind of even this kind of, so if I have if I have a sufficiently good, let me translate this into this idea of model. So I said that for non-convex optimization, we want to approximate things with simpler models at each iteration. So if I can still get a good model, even if I don't have actual first-order information, if I can get a good model on each iteration, derivative-free optimization algorithms tell me I can apply the same kind of thing as before, pretty much. But we go a step further than this and say, what if I have these models only with a certain probability on each iteration? So I just know this, that it will be sufficiently good with a certain probability. Let me try to make this a bit more concrete. Let's assume I get my local model by sampling of function values, random sampling of function values. If I do this sampling accurate enough, only with a certain probability, greater than a half, I can actually, I will tell you, apply the previous frameworks as before. So I really need very low accuracy. The other possible approach here would be, let's say I can do finite differencing to calculate gradients. And I compute them in parallel, and I send them to different processors to each compute a finite difference. Now, if I have failure in these processors, and some of these processors fail to return the finite difference to me, can I still continue with the algorithm? So ignore the failed processor and just keep going. The answer is yes. In fact, you can get failure, provided your failure is less than a half, okay, which is pretty, I think, a pretty relaxed condition, you can continue with these methods. So I will talk about this kind of approach. So let's say we can still take the cubic regularization, and now I'm not going to have any gradient here that's the true gradient, and here also I have approximate second order information. So this is now a stochastic algorithm, and what happens is that I assume that I have a sufficiently good model with a certain probability. I don't know in a given iteration if I have a good model or a bad model, because it happens probabilistically. But I know that it will happen with a certain probability. And what I can say then is that this probabilistic cubic regularization framework actually maintains the same rate of convergence as a function of the accuracy, and the only thing that changes is that this rate is multiplied by a constant factor of the probability of the model being good. And provided this model is good with probability greater than a half, I can keep running these methods. So these methods are actually extremely robust to failure, to inaccurate information. And the message is just keep using them. And provided you have some guarantee that from time to time you get a good enough model. Right. So I have a bit of time just to say a few words that we can do other frameworks with occasionally accurate data. So in fact, we can analyze pretty much a lot of standard methods in optimization where you relax this assumption of having accurate problem information. This is a bit technical again, I'm sorry. So what I'm talking about is when I just do, say, a first order method, and I have an approximate gradient here, and I'm just going to go a certain fraction along it, and then I verify if I make progress or not. And if I don't, then I'm going to cut my step, and if I do, I'm going to increase it. And again, for this framework, we recover, if the model is good with probability greater than a half, the first order model, then the complexity maintains the complexity of first order methods of epsilon to minus 2, and again, it's just the constant multiple depending on the probability of the model being good. So the complexity is just the standard classical complexity multiplied by just a constant factor. Okay, so just to make even more concrete, I said we can do random sampling of function values to construct this kind of sufficiently accurate models with a certain probability. But we can also do things like stochastic gradient and batch methods. So these are methods that people in machine learning use a lot. And but they use them with, say, a linesearch framework where the step size is very fixed and it decreases to 0 at a very fixed rate to control the variance. I mean, there is a reason for it. But most of those methods are used for convex problems. What we are saying here is you can do a variable step size, which is better from an optimization point of view. You should always do a variable step size because you can then make faster progress locally. So you can do variable step size, and you can apply it to non-convex problems, say like deep neural networks. So in that context of machine learning, we are saying you can use more of the classical frameworks and be confident that they actually should perform well. So we were able we can actually show that if you have a batch sampling or stochastic gradient framework, we can show that those local models resulting from those frameworks fit into our approach. They do give you this local model that's good with a certain probability. And then, so our methods do apply to that context as well, to those methods as well. Okay, so I've talked about, in fact, what we can do is we have a very general framework in which if you know that your model is good with a certain probability, your local model, then we can tell you what the complexity of resulting methods is. So in fact, there are a lot of possibilities there. The question is which one of them would be better numerically. This is something that we are looking at the moment in an effort to try to convince maybe a machine learning community that it would be worthwhile to move to sort of more classical frameworks, but that would still not be as expensive as classical frameworks. The other thing that is important here is that in everything I've just said, I've assumed that I have at least accurate function values. But for stochastic optimization, you lose that. So we were actually able to translate these results with inaccurate model, with probabilistic models, for the case when we don't have accurate function values. So in the true case of stochastic optimization, with similar results, more restrictive but similar results and guarantees. And that's another area where my attempts would be to try to convince the people working in machine learning that there is value into looking more at classical optimization frameworks and applying them in a cheaper way than classical frameworks to the machine learning problems. Okay, that's it.